Hello friends, I am Yugen Kulkarni. We are studying current electricity from 12th physics. In this video, we are studying meter bridge. This is the diagram of meter bridge. This is modified version of Wheatstone bridge, or we can say meter bridge is the application of Wheatstone bridge. Now we will see how. Here you can see the X. Here in this left gap, that is LG, we will place the unknown resistance, and in the right gap we will place a resistance box, and from which we can change the resistance of this resistance box, or we can say this is a variable resistor. Now look at this galvanometer, and this is jockey. So this is the variable contact, so we can drag the contact, we can change the contact here. This is the another arm of the circuit, AD and DB. So this length of AD, which we will call LX, and the length D to B, which is LR, contribute to the resistance in the bridge. So you can see this is one arm, this is another arm, this is one arm, and this is another arm. So there are total 4 arms, as we have seen in the Wheatstone bridge, and one of the arm is constituted by the unknown resistance, the resistance which we have to find out. This Wheatstone bridge is called as meter bridge because this consists of a 1 meter length of the wire, which is composed of 2 different resistances, or we can say that there is only 1 meter scale, 1 meter long wire, which we divide into 2 forms using this galvanometer and this jockey. That 2 forms will be labeled as LX and LR. These are the lengths of that respective portion of the meter scale or 1 meter long wire. Now below you can see the rheostat, that is the variable resistor. Then there is a key K, where epsilon is the battery. This sign, the arrow in the middle of the resistor, says that this resistor is variable, so that can be a rheostat. Now this is a portion of your textbook. So here you can see the diagram, and here you can see the derivation, how we will calculate the unknown resistance. So in the Wheatstone bridge, we have seen that these resistances are in ratios. So X divided by R will be equal to the resistance from A to D and the resistance from D to B. So this will be in the ratio at the null point. So what is the null point? When the galvanometer will show 0 reading or 0 deflection, then that point is called null point or 0 deflection point. So at that point we will note length AD and length DB. So we know the resistance should be in the ratios. Now how we will find out the resistances of these portions AD and DB? So there is one formula for resistance, which is equal to rho into length divided by area. So rho is the resistivity of that wire. Resistivity only depends on the material of the wire. So we are not going to change, and this is appearing in both resistances for R A to D and for R D to B. So when we take ratio, this rho will get cancelled out. Now let this wire be uniform, that is, it has a uniform cross section, that is, the area of the wire is constant or same throughout the wire of 1 meter length. So we can cancel this area term also. So using this we can get X divided by R is equal to LX divided by LR. So LX is the length of this portion and LR is the length of this portion DB. Now we can rearrange this and take R to the RHS. So here it is divided, so it will go here and get multiplied to this ratio. We can even call this as x is equal to Lx divided by 1 minus Lx, because the total length is equal to 1 meter. So we can write it Lr is equal to 1 minus Lx, and so we can calculate the unknown resistance. Now we will see the Kelvin's method. What is Kelvin's method? This is the application of meter bridge. Here, instead of having unknown resistance, we have replaced this with galvanometer, and we are not used here any galvanometer. So what is the purpose of the Kelvin method? Everything else is same. There is variable resistor, there is 1 meter long wire, and we will have this D point where the galvanometer will show null deflection. So that is, we will get two portions of this wire, Lg and Lr. So Kelvin method suggests that if we replace the resistor by this galvanometer and then get a point D where the galvanometer will not show zero deflection, but it will show no deflection. Suppose it shows 10 degree, then after changing the position of D slightly, this position will remain 10. Then we can say that we are getting the null deflection. Here in the previous case there was zero deflection, but in this case we will just call it null deflection, but the galvanometer will not show exactly zero because the current is flowing through this galvanometer. But what we will see is the deflection is not changing. At that point we will record the D, and then we will take the reading of Lg and Lr, and as previous case the ratio, we will take the ratio and multiply with this variable resistor, whatever the value will be here, and so we will get G like this. So G by R, instead of X by R we are using here G by R, and the resistances we know, which we can replace by L because it is a ratio. So we will finally get G by R is equal to Lg divided by Lr, or we are taking this in centimeter, so we can write this as Lg divided by 100 minus Lg, because total length of the wire is 100 centimeter, that is 1 meter. So using this formula we can find out the unknown resistance of galvanometer, that is internal resistance of the galvanometer. Post office box is the one more application, or we can say the practical form of Wheatstone bridge. So here you can see A to B is resistance P and B to C is the resistance Q, and then A to here we will find out the key. Up to this point we are having resistance R, and then we are arranging this unknown resistance here, which we can call S or X. By taking the same fashion we will adjust R and X such that this galvanometer will show null deflection.